Well, thanks for coming to our July general meeting for the East Bay Astronomical Society. And it's kind of an exciting night around here at the Chabot Space and Science Center. Tonight is actually our first member event in quite some time. There was a members only telescope viewing event that was scheduled for tonight. And one of the things that's going on is live casting this presentation out on the Chabot deck, in addition to waiting for nightfall and some looking through the telescopes. So it's always a good sign. We're happy to see that happening. We hope all of you have been well, and I'm looking forward to the reopening of the Chabot Space and Science Center in November. EAS has been talking about how we're going to be reopening our programs. We have the Telescope Makers Workshop, we have our regular outreach events, we have our Loader Scope program, we have our members only viewing nights. All of those things are under discussion right now on how we're going to reopen those activities and when we're going to reopen those activities. So keep an eye on your email as we start getting back to our normal course of events. We will, of course, let all of you know. And we want to thank you for your support over the last couple of years. We know that you always have a choice on which memberships you choose to keep active, and we're just thrilled and honored that that so many of you have decided to continue to support the East Bay Astronomical Society and the Chabot Space and Science Center. So without further ado, Dave, where are you? Are you here?
I'm here.
Dave. All right.
There
I
I am.
don't see you.
There I am.
Now I see you. There you are.
It's me.
How have you been?
Pretty well. How about
Good.
you?
I'm doing okay.
Okay.
Uh,
Should I introduce Mark, or should we just continue the
Uh,
chit chat?
no, let's introduce Mark, and we can get started unless you have something pressing you need to say.
No, nothing else pressing for the moment.
Okay.
Still don't have a speaker for next month, but whoever it is going to be really good. So
All right.
I want to tell you
Perfect.
about that.
That's good to hear.
We got some other great programs coming up. Anyway, I want to make this introduction brief because I think Rich and Mark are under the false impression that I talk too much. Where they get an idea like that, I'll never know. Anyway, so Rebecca, Rich, Alan, and I heard this talk at RTMC, and we were all very impressed. I then immediately decided that I wanted Mark to speak to EAS. And as you listen to Mark tonight, I think you'll recognize a kindred spirit to many of us. He became interested in astronomy at the age of 4 when he saw a meteor flash overhead. And he's worked on a number of missions at JPL. And in addition to Dawn, the mission he's going to talk about tonight, he worked on Deep Space One, which is a really neat mission. There's a great story to that. Voyager, and the Mars Sample Return mission he's working on as well. And he is also JPL's chief engineer for mission operations and science. So when you ask him a question, be really respectful, because he's really important. Just kidding, Mark. And finally, if you enjoyed tonight's talk and want to learn more about Mark, I highly recommend that you listen to his very inspirational TED Talk. It's entitled, "If It Isn't Impossible, It Isn't Worth Trying." There's a link to it on our society's website under news and events. So it is my very great honor to introduce Dr. Marc Rayman in tonight's talk, NASA's Dawn mission to the asteroid belt. Mark, go ahead.
Thank you, Dave, for that kind introduction. I really appreciate it. And thank you, Rich, as well. And I appreciate everybody attending this evening and letting me tell you about the Dawn mission. So I will just ask Dave or somebody to stay on long enough to confirm that you can see my PowerPoint here. Can you, Dave?
I can see. To boldly go.
Okay, good. So as you heard, I'm going to tell you about the Dawn mission, and I work at JPL, which is run by Caltech for NASA. Excuse me, but there are many organizations around the country and indeed around the world that were involved in this project, including even UCLA, not too far from where I live, near Pasadena. But before I start telling you about the Dawn mission, I want to give you a little bit of context and take you back in time to talk about what astronomers knew about the solar system in 1800. So this is a view, conventional view of the solar system, looking down on it with the sun in the center And you can see the orbits of the inner planets, including Earth and Mars. And as we go up farther out, Jupiter, Saturn, and Uranus. And apart from some moons and an occasional comet, this is pretty much what astronomers knew about the solar system in 1800. And in fact, even this was quite a recent picture. It was a modern picture because Uranus had only been discovered in 1781. Of course, the planets from Mercury to Saturn were known even to ancient astronomers. But because of Uranus's discovery, this same picture could not have been drawn even 20 years earlier. So this was, at that time, a modern view of the solar system. Well, then in the beginning of the 19th century, along came these two gentlemen, Giuseppe Piazzi and Heinrich Wilhelm Olbers, and they got the new century, the 1800s, off to a great start because they discovered new planets. Modern astronomers had only ever discovered one planet, so this was truly quite a significant finding. And I'm going to show you high-resolution photographs of the planets they discovered, the bodies they discovered. They're here, Ceres and Vesta. Ceres on the left, the goddess of agriculture and grain. She's often depicted with her crown of grains and holding her harvest bounty. And in this case, she's holding a scythe. Different artists choose to show different farm implements. That's simply an artistic choice. But if you had cereal this morning, then you have an etymological connection with the good goddess Ceres. Vesta on the right, named for the Roman goddess of hearth, home, and family. It's interesting. Relatively little is known about how Vesta figured into Roman mythology because she was worshipped privately in the home. Now, you may have heard of the Vestal virgins who were associated with her, but I'm talking about specifically the goddess Vesta herself. And in fact, she's rarely depicted in art. But when she is, she often has this very stern look on her face that you can see here. But one of the things I hope to convince you of this evening is that the solar system body is a much happier place than the good goddess Vesta. So those are the bodies that Piazzi and Olbers discovered. And now here again is the picture of the solar system where I've zoomed in. So Jupiter is the outermost planet. And you can see Vesta and Ceres fit very nicely into the gap between Mars and Jupiter. And along with two other bodies, for well over a generation, were considered to be planets. And in fact, if it's interesting, if any of you who are watching now had attended one of the East Bay Astronomical Society or presentations or visited the Chabot Science Center, say 200 years ago, you would have been different in two interesting ways. One is you would have been slower to check email on your smartphone, but the other is you would have learned that Vesta and Ceres are planets because that's how they were known at the time. But as the 19th century progressed, science and technology progressed, and eventually the solar system started to look more and more and more like this, where now I've added not the orbits of these other bodies in the vicinity of this region between Mars and Jupiter, but if you take a screenshot and devote your time later to verifying this, you'll see that I've added 10,480 dots, excuse me, to indicate that number, the location of that number of asteroids. Now, I should tell you, we know about many, many, many more asteroids than that. I'm only showing you the ones that are larger than about 5 miles or so in diameter, because if I showed you all of the ones that we knew about, this would be just nothing but a solid yellowish green and you wouldn't be able to see anything else. But what this picture tells you is this part of the solar system is very different from the inner solar system. And in fact, if I zoom out, you can see even more clearly that this part of the solar system really is different from the rest of the solar system. And of course, we now call this region the main asteroid belt. And Dawn's mission is to fly out to that part of the solar system and explore some of the bodies there. Now, I think when most people think of asteroids, they think of chunks of rock, the size of buildings or mountains. But you can see with this photograph of Vesta that Dawn took, and all of the other asteroids that spacecraft had visited, Vesta is really of a very different scale from all of these other bodies. And of course, the ones down in the box at the bottom, particularly Bennu, which the OSIRIS-REx spacecraft recently took a sample from, and Ryugu, which Hayabusa 2 collected a sample from, are so small you may not even be able to see them in the box, but they are there. It shows you, again, that Vesta is very different. And in fact, if I bring Ceres in, it also is of an entirely different scale. And so we can look at this in a different way by comparing Vesta and Ceres. So here they are again. Vesta, about 350 miles in diameter. Ceres, almost 600 miles in diameter. Here they are compared to the two largest asteroids that spacecraft had visited prior to the Dawn mission. Matilda is the largest asteroid United States spacecraft had visited. A European spacecraft had flown by Lutetia. And in the interest of full disclosure, I should tell you that I exaggerated the size of Matilda here. I made it 1 pixel, so of course you could see it. But again, this says that Vesta and Ceres are not at all like these little chunks of rock. They're really much more like bodies other places in the solar system. And in fact, I'm sure you remember that in 2006, the International Astronomical Union created a new category of solar system bodies, dwarf planets. And oh my goodness, everybody thought this was awful. How could Earth be so inconsiderate? How could we be such an interplanetary bully? Why didn't we consider poor Pluto's feelings in the matter when we called it a dwarf planet instead of a planet? Well, whatever you think of that decision, whatever you think of it, at the time it was decided Pluto was actually the second known body to fit in that category, because Ceres, discovered 129 years earlier, was actually the first dwarf planet discovered. It satisfies all of the attributes of a dwarf planet. It just so happens that you and I, or at least most of you and I, grew up during that narrow window in human history when Ceres was no longer called a planet, but Pluto was temporarily being called a planet. At any rate, when you look at pictures like this, it's somewhat deceptive. In fact, Rich and Dave and I were talking about this earlier, because California is flat, right? But Vesta and Ceres are round, three-dimensional objects. They're not flat like the state of California is. And in fact, Vesta has well over twice the surface area of California. And so we can go into the third dimension by comparing the surface area of Ceres with that of the continental United States. So the map at the top is Ceres from Dawn, and I'll show you more pictures of it. And of course, these pictures are in what astronomers and many of you know about, called false colors. It doesn't show it for Ceres or for the United States the way, of course, it would look to your eye. It encodes some other scientific information, which isn't pertinent here. But I've drawn them to the same scale. And so you can see, sure, Ceres isn't as large as the United States. Ceres isn't as large as Earth, but it's still a big place. It's 37% of the area of the continental United States. And if you just think about how vast and varied and frankly beautiful the geography and topography and geology of our country are, it suggests there's an opportunity for a lot of things to see and a lot of diversity on a place like Ceres. And to me, that's part of what's so exciting about sending a spacecraft out there to explore, this alien world. which I think is really cool. And so that's what we did. And here's a view of Ceres, or views of Ceres, from the Dawn spacecraft. And you can see it has craters. You can see some linear features, some other strange shapes. But the thing that stands out the most are these bright areas like this one. And here's a closer view of this. And I think these sorts of things were really, really fascinating. I mean, this crater here is 57 miles in diameter. So this is a big, big structure that we're seeing here. And it was one of the first things Dawn was able to make out as it flew in to Ceres. Whoops, I'm not sure why. I've seen this in other Zoom meetings where the slide advances even when I'm not touching it. I'll come back to that in a moment. And when I say in other Zoom meetings, I mean other presenters in other Zoom meetings. So there's something funny going on here. But anyway, when Dawn first saw this, it was, to me, sort of like a Ceres was casting almost like a lighthouse, right? Casting a beacon out onto the interplanetary seas, just inviting a cosmic explorer to come in for a closer look, which of course is exactly what we did. But I'll also tell you, when we started returning pictures like this, one of the most common questions that people asked was, could this be lights of an alien city? And in all honesty, I mean, we're all interested in astronomy and science and technology. I find questions like that really sort of demoralizing or disappointing. I mean, it takes the best of humankind's science and engineering and myriad other skills and dedication and commitment to be able to put together a mission like this and fly it literally billions of miles to get pictures like this, and then to ask, could this be lights of a city on Ceres? I mean, it just makes you wonder what's happened to critical thinking. I mean, after all, the spacecraft is just getting to Ceres. How could we possibly know whether the Sirians live in cities, right? Maybe they live underground, so their light wouldn't leak out. Maybe they live in large rural communities. So there's just no way we could know something like that at that early stage. But anyway, we did go in closer, and now I'm going to zoom in on this area, and I'm going to show you still more detail of this later on. But you can see it's quite a complex and fascinating structure. And I'll not only show you more pictures of it in a moment, but I'll also tell you how it formed and why it looks the way it does. But I also want to zoom in a little bit on this neighboring area. And this, again, is so strange. I mean, look at that structure in the center. Looks like a pretty regular square there. And it's just a really strange, truly alien, exotic landscape, which again is part of what I love about sending a spacecraft to see something we've literally and truly never seen before. So now let's look at it here from a different perspective. So we're looking at it from the south, looking north, and I'm going to zoom in a little bit. And before I zoom into more of that bright material, I want to show you this just because, again, I think this is cool. And that crater wall is more than 2 miles high. And here you can see a closer view of it when Dawn flew down really low. And I just think the detail on this is really fascinating to see these structures projecting out from this steep landscape. And I'll show you some related structures later on. And now here, which we saw a moment ago, zoom in even more to this strange square there. And let me also, I hope you can actually see my cursor here. Just wanted to draw your attention to this thing. So this is a V-shaped groove. When I say groove, I mean, you can see this there's the scale, 1/2 mile. So this is many hundreds of yards across, but it's a pretty sharp V. And look at this here. Looks like perhaps something flowed down a crack there. And now we can zoom in still more. And now we've been looking from the south to the north. I want to flip us around and look from the north to the south. And now we're going to take a more detailed look at this. You can see this here. And once again, so it turns out this is pretty flat level here, and this is a steep slope. And here you can see this material flowed down cracks here. And so what we now understand is that Ceres at one time was covered with a liquid water ocean. Now that ocean, for reasons I could explain, has long since dissipated, but much of the water is still is still there at Ceres, much of it frozen, but there may still be liquid water deep underground. And some of it is not actually that deep. And so when this crater was formed, it tapped into an underground reservoir of water, which came up through cracks to the surface. And you can see many of the cracks right here, these fissures in the ground that allowed water to come up, and it's salt water. So it got onto the surface in the cold vacuum of space there on the ground at Ceres. The water froze and then sublimated, that is, the water molecules dissipated, but they left behind the salts that were dissolved in them. And so what we're seeing are essentially salt flats, salts deposited on Ceres from water that came up from beneath the ground in very, very recent geological time. And in fact, it's possible that this process is ongoing even now, because our instruments, our sensors, detected minerals there that should only last perhaps hundreds or maybe not even that long of years before decomposing. And so this is very, very recent. And now I'm going to show you an animation of this same area where, again, it's color coded, that is false color, but the pink or red there, I'm not good with some colors, but that color shows some of the most recent material, and we can gain a little bit of perspective on what it looks like as we move around there. So now I'm going to zoom back out, just another view that I just think is a really cool one, again, showing this brilliantly glowing area. But I want to show you still another view, higher up view of Ceres, and draw your attention to that bump on the top. That bump is actually the tallest mountain on Ceres. And it turns out it's a cryovolcano. Cryo, cold, volcano, of course, you know what that is, because on Ceres, being farther from the sun and smaller than Earth, doesn't have the same sources of energy that Earth has, which has a vast inventory of radioactive materials, which provide internal heat. Ceres still has some of that, and Ceres doesn't get as much sunlight, but it still has enough that this volcano built up, and instead of erupting with what we would call magma on Earth, we call it cryomagma on Ceres. So it's a mixture of water, dissolved salts, rock, so you could call all of that mud. It comes up and forms this strange structure. I'm going to show you now a view looking from over that crater in the upper left. There we go. Geologists have detected about 20 volcanoes on Ceres. This is just the most recent. And so this isn't a photograph. This is synthesized from the data we took. But I love this view because from the low point in that crater to the summit of Ceres is only about 10 miles horizontally, but almost 25,000 feet vertical elevation gain, 25,000 feet. And so I'm hoping to suggest that the East Bay Astronomical Society and the Chabot Science Center join me for a hike there someday, because in the 1/40th gravity on Ceres, I think 10 miles, a 10-mile hike and a 25,000 foot vertical elevation gain shouldn't actually be very hard. I think it should be pretty neat. So I hope we can all do that together sometime. Now, this is another crater wall on Ceres, a different crater, and you can see the scale there. And I want to draw your attention to something else. Now, this crater is judged to be about 1 billion years old. I shouldn't say judged, it's measured to be about 1 billion years old. And you can see this trail of small craters down the crater wall. And look at the bottom. There's the rock that bounced down that wall and stopped at the bottom. And you can see the trail from that event where it just bounced down the wall. And in fact, there's another long trail of craters. And sure enough, there's another one at the bottom. And you can see many more there. And I didn't even circle all of them. One of them, you can tell, got a hole in one. It turns out that some of these happened in just the last few, perhaps tens of thousands of years in this billion-year-old crater, showing that Ceres, again, is geologically active. This isn't just a dead world. And in fact, higher up on the crater wall, you can see more that are ready to fall some point, have not yet succumb to Ceres gravity, but at some point they likely will, and they'll create their own trails for us then to appreciate, for future explorers to see. So that's just a few of the cool things on Ceres. Let me turn my attention now to Vesta. And here it is in the best picture we had prior to the Dawn mission. So this was taken with the Hubble Space Telescope at the end of the 1990s. And, powerful as Hubble is, Vesta is still pretty far away. And so it's not the greatest picture, but it shows you, excuse me, that it's sort of planet-like, especially if you start here and follow the shape around like this. It's even got a little bit of flattening at the pole, just like our planet does. And it looks planet-like until you get around to here, where you would expect a smoother curvature here if it were a more conventional planetary shape. And so these pictures led planetary geologists to conclude that what we're seeing is a body that's shaped like a planet with a big crater there near the South Pole and a mountain in the center of the crater. And you may have seen other pictures of big craters on the moon or Mars, or even some of the ones that were there on Ceres. Often craters have a mountain in the center. And many of you have seen that yourself with your own telescope looking at the moon. And the reason for that is that the way you make a crater is you have a big piece of interplanetary debris. It comes screaming down into the surface, and it hits with so much energy that it melts the rock. And the rock sloshes away and then sloshes back. And as it does, and it sloshes back, it's cooling and it solidifies. And so the mountain in the center of the crater, to me, is like a snapshot of the process by which that crater was formed. And so I want to show you an animation of how this crater was formed on Vesta. Now I know with Zoom, sometimes these things are jumpy, but I'll just hope it comes through from how a big impactor created this crater. So here's an impactor, and there's Vesta before the impact, and now here's Vesta after the impact. And this impact was so powerful, it excavated a tremendous number of rocks, something like 1% of Vesta's mass, threw that out into the solar system. And some of those rocks even made their way to the part of the solar system where you spend most of your time. And some of them then even were pulled in by Earth's gravity. And as you well know, when you're out on a nice dark night and you're lucky enough to see a meteor, that's something burning up from space. And in fact, Dave mentioned earlier that that's how I became interested in astronomy and space when I was 4 years old. And what you may not have appreciated is that sometimes what you're seeing may be a piece of Vesta burning up. Now, when I say that, I'm not just being poetical or clever, although I am poetical and clever. I'm being serious because this is a picture of a meteorite that came from that impact at Vesta. And I took this picture myself of a meteorite in a museum. And in fact, if you can see in the little window here, these are very common. I even have one meteorite here in this box, and I apologize for the reflections on the plastic there, but they're so common, one of them just landed in this box. It turns out that we now know, thanks to Dawn, that about 6%, I mean, think of this, 1 out of every 16 meteorites seen to fall to Earth came from that one impact at Vesta 1 billion years ago. And in fact, there are only 3 solar system bodies to which we have linked specific meteorites: the moon, Mars, and Vesta. Those are the only bodies to which we have linked meteorites. And yet we have far, far, far more meteorites from Vesta than we do from the moon or Mars. In fact, even accounting for the more than 840 pounds of material that Apollo astronauts brought back from the moon, we have more material, more identified material on Earth and even in laboratories from Vesta than we do from the moon. I think that's really cool. So that, the opportunity to study this material in its geological context with Dawn is just another one of the neat features of this mission. So that's the meteorite connection, but let's get back to Vesta itself. So here again, it is in the best view we had prior to the Dawn mission. Then Dawn showed us this, and of course, we got in much closer to get even better views. And you can see that large mountain at the bottom and the crater that it's in. And you can also see this triplet of craters, which we nicknamed the Snowman, mostly because we're not very imaginative. And just as we took 70,000 pictures of Ceres and more than 30,000 pictures of Vesta, unfortunately, I'm a little disappointed because Rich and Dave didn't allocate me enough time to show you each individual picture we took. So instead, again, I've put these together into an animation to show you what it would look like if you were lucky enough to be in the vicinity of Vesta and see it. And so here's what you would see. And one of the first things you might notice is that the northern hemisphere is very densely cratered. But as we go to the south, you'll see that it's much smoother, much more lightly cratered. Why? Because that big impact deep in the southern hemisphere sprayed out so much material, some of it landed back on Vesta, and erased the cratering history. It also created those canyons that you saw near the equator. There are more than 90 of them that rival the Grand Canyon in size. They're from that big impact. And here you can see part of the crater wall that's still left. Some of it, of course, has since been destroyed by impacts over the 1 billion years since this impact. And now we're looking down on this mountain. The mountain is 110 miles across at the base and rises to more than 2.5 times the height of Mount Everest. And in fact, the crater wall rises to 3 times the height of Mount Everest. So topography completely unlike anything on your planet. So again, I keep coming back to this. To me is what's so cool about exploring alien worlds, is getting to see things that are truly unlike anything that we've seen elsewhere in the solar system. And I want to show you still another view, which again, I just think is really cool. There's the triplet of craters, the snowman. Here are some of these canyons caused by the impact. And I should point out, these canyons were the result of the impact at the South Pole and the energy then reverberating, all of Vesta itself reverberating, then breaking up this ground hundreds of miles away. And this is also a nice view because here you can see the densely cratered northern hemisphere and the transition to the more lightly cratered southern hemisphere. So that's a quick overview of Vesta, but let me give you the overview of the Dawn mission itself. So we launched from many people's favorite planet, Earth, in September 2007. And we used a big rocket. I just threw that in to help you stay awake on a Saturday evening. On our way out to the asteroid belt, we flew by Mars for a gravity boost. You've heard of these sort of things before, a slingshot effect. Essentially, Dawn stole some of Mars's orbital energy around the sun to help fling it out farther into the solar system. So NASA, JPL being environmentally responsible, we believe in energy conservation, or the conservation of energy. And so for Mars to speed Dawn up, Dawn had to slow Mars down. And so as a result of Dawn flying by Mars, Mars now orbits the sun more slowly than it did before Dawn got there. And so if you're keeping track, Mars orbits the sun now more slowly by a velocity of 1 inch per 180 million years. That's how much we reduced Mars velocity. Fortunately, Dawn has lower mass than Mars, and so we got a larger gravity boost. Excuse me, in July 2011, we got to Vesta and didn't just fly by it as many spacecraft do. Instead, we went into orbit around it, stayed there for 14 months, then broke out of orbit, traveled for another 2.5 years to get to Ceres, and went into orbit around it. And at each destination, Dawn collected a comprehensive set of measurements. And I won't take the time to walk you through them there. I'll just point out that we collected a wealth of data at each body. But this picture illustrates, I think, several interesting things. One is Dawn is the only spacecraft ever to orbit an object in the main asteroid belt. It's also the only spacecraft ever to orbit a dwarf planet and the first spacecraft to reach a dwarf planet. But to me, more interesting than any of those is that in well over 60 years of space exploration, Dawn is the only spacecraft ever to orbit any 2 extraterrestrial destinations, which when you think about it, really is, really is a surprising thing. It seems like a very obvious kind of mission to do. Go to a body, study it in detail, and then go to another one and study it. It seems like a very natural sort of mission that scientists would want to undertake. And it's not as if nobody ever thought of it before, right? It happens in science fiction all the time. Go to some body, do whatever you're going to do there, beat somebody up or make out with them, and then go to some other world and do the same thing. And yet, in all this time, no spacecraft, no mission prior to Dawn or since ever even attempted such a mission. So why is that? Why had no mission ever attempted doing that? Well, the reason is because until recently, engineers were confronted with a problem. And they were confronted with the same problem that this guy was. That is, they just didn't have the technology to carry it out. It turns out that to send a spacecraft to a distant solar system body, go into orbit, maneuver in orbit to collect your data, break out of orbit, fly someplace else in the solar system, go into orbit around that body, and then maneuver there was far, far, far beyond the capability of conventional propulsion systems. And so a number of years ago, I got together with some colleagues, at JPL, and we asked, how can we travel around the solar system more easily and less expensively? And our answer to that was ion propulsion. Now, if you're like me, and I actually know that some of you are, the first time you ever even heard of ion propulsion was in science fiction. And in fact, this is the Star Wars TIE fighter that Darth Vader and the evil Empire used to fight Luke Skywalker and the members of the Rebel Alliance. And in the Star Wars universe, the TIE fighter, TIE, stands for Twin Ion Engine, because this was the most futuristic, coolest, advanced technology that George Lucas could think of. And to me, one of the rewards of turning this technology of working on a mission like this is turning that technology, that science fiction, into science fact. And so this is an artist concept of Dawn using its ion engine as it flew into orbit around Ceres. And here's a photograph of an ion engine operating at a vacuum chamber at JPL here just outside of Pasadena, where I work. And you can see it really does produce this cool blue glow like in science fiction movies. And the reason for that is for the propellant, we use xenon, which is like helium or neon, but heavier. And xenon just happens to glow blue, like neon and neon lights just happens to glow orange. And this system has 10 times the efficiency of conventional rocket propulsion. So this would be like your car getting 300 miles per gallon. And that's what allows us to undertake missions that would be not just difficult, but impossible, truly impossible with any other existing technology. But now, while this system is very efficient, the thrust is also very gentle. We only flow a very small amount of propellant through the engine at a time. And in fact, I'm going to do an ion propulsion experiment right here in the safety of my house. And you can do this yourself. This is pretty safe. That is, the ion engine pushes on the spacecraft as hard as this piece of paper pushes on my hand. And yet, in the zero gravity, frictionless conditions of space, gradually the effect of this thrust builds up. So it turns out it would take Dawn 4 days to accelerate from 0 to 60 miles per hour. Doesn't exactly make you think of a drag racer. But instead of thrusting for 4 days, if you thrust for a week or a month or a year, or as Dawn did for almost 6 years, you can achieve fantastically high velocity. And so this is what I like to call acceleration with patience. And if you're patient, and I'm a very patient guy, this is a great way to explore the solar system. And this is really the key to what allowed us to undertake this mission that, again, would have been impossible with any other existing technology. And it's also what allowed Dawn to change its velocity by far, far, far more than any other spacecraft had ever done with its own propulsion system. Now, I told you that ion propulsion has been around in science fiction for a long time. I mean, I showed you that Star Wars picture from the 1970s. I don't have time to give you the entire history of ion propulsion, but I'll tell you it goes back even well before Star Wars. But in the interest of time, I'm going to stick with just the Dawn mission here. And there's an artist concept of the Dawn spacecraft. And the first thing you notice is it's dominated by these huge solar arrays. These, of course, convert the light of the sun into electrical power to run all of Dawn's systems. And we need such large solar panels because Dawn traveled far from the sun. Sunlight is weak, so you need a large area of solar cells to capture enough sunlight to produce the electrical power to operate the spacecraft systems. And those ion engines are power hungry. They take a lot of electrical power to work. But we also, of course, need electrical power for sensors, computers, radio, heaters, and all of the other systems. And these solar arrays are so big, they're 65 feet from wingtip to wingtip. That's the distance from a pitcher's mound to home plate in a professional baseball field. And so at the time we launched Dawn in 2007, this was the largest wingspan of any interplanetary spacecraft NASA had dispatched into the solar system. You can also see here Dawn's main antenna, 5 feet in diameter. That's how we communicate with the spacecraft from across the solar system. Here's an ion engine. Here's a second ion engine. And oh boy, what do you know? There's a third ion engine there. So we do the Star Wars TIE fighters one better. Now that's an artist concept. Here's a photograph of the spacecraft when it was in a vacuum chamber. It's not a vacuum chamber, a clean room here on Earth when it was being assembled. And this is one of the solar array wings here. This is the other. And they're folded up because you can't fit a 65-foot wide spacecraft inside the nose cone of a rocket. And so after launch, when the spacecraft separated from the rocket, it opened up these solar arrays, stretched them out. I think of it as being like a big celestial dragonfly spreading its wings and taking flight. Here's one of the ion engines. This 1 foot diameter metal grid has more than 15,000 little holes in it through which we shoot the xenon ions in order to provide the propulsion. We shoot them out at up to 90,000 miles per hour. And that's what provides this very efficient push back on the spacecraft. These are some of the sensors on top, and the xenon that I just mentioned is stored in a tank inside the main spacecraft structure here. And because I've mentioned xenon a few times, I thought I ought to show you a photograph of xenon. So this is actually my pet chameleon named Xenon. Because of his color, he has sort of a cosmetic affection for ion propulsion. But to tell you the truth, he gets a kick out of being included in my public presentation. So after this Zoom meeting is over, when I go downstairs and tell him a bunch of people way up in the Bay Area got to see a picture of him today, he's going to think that was pretty cool. But here's another view of the spacecraft. So here again, the main spacecraft structure. This is the 5 foot diameter main antenna. Some of the sensors on top for studying Vesta and Ceres. There's Tom. This is one of the solar array wings. Each wing on its own at 27 feet is the width of a singles tennis court. So this is a big spacecraft. And I don't know about you, but I think spacecraft are neat to look at, right? They're cool. Spacecraft, I think, they're cool to look at. But to me, cool as spacecraft are, I think even cooler is what we do with them. And so I want to spend a little bit of time talking about that, because we use spacecraft to go far from home. This, of course, is home. And to the accuracy I can do PowerPoint, so with that caveat, this is low Earth orbit on the scale of Earth. It's space, but is not very far away. In fact, the distance from the surface of Earth to low Earth orbit is less than the distance from all of you to me here in the outside of Los Angeles, near Pasadena. So it's not very far away. And that's where the International Space Station, the space shuttle when it was flying, and many other spacecraft live. So they're in space. They're not very far away. So excuse me. So let's zoom out a little bit to the next scale and introduce geosynchronous orbit. And geosynchronous orbit, I'm sure some of you know this, but for those of us who don't, let's just remind ourselves, at the altitude of geosynchronous orbit, a spacecraft takes 24 hours to orbit Earth, 24 hours to go around once. Well, Earth also rotates in 24 hours, which means that the spacecraft is always over the same point on Earth. Or put differently, from the surface of Earth, the spacecraft always appears to be at the same place in the sky. And that's why geosynchronous orbit is a very convenient location for weather satellites, communication satellites, and other satellites that you want to have a fixed view of the ground, or where you want to have an antenna on the ground pointed at the satellite and not have to keep moving the antenna to track the satellite because it's always at the same place. And at more than 22,200 miles, geosynchronous orbit is far away. You can see it's far even compared to the diameter of our planet. So geosynchronous orbit is a long way away. And in the more than 60 years of space exploration, the overwhelming majority of spacecraft have gone to somewhere between low Earth orbit and geosynchronous orbit. Now, with that context, let me go to the next scale. I'll put the Earth there. There's geosynchronous orbit. Now let me bring in the moon and put the moon up where it belongs. The moon is really far away. The moon is 10 times the distance to geosynchronous orbit. It's 30 Earth diameters away. The moon is 250,000 miles. So the moon is really far away. And I'm sure some of you have, heard myths, legends, tales from our ancestors that long, long ago, humans traveled to the moon. That's so long ago, it's hard to know whether that's true. And people don't do that today, right? People don't do that. People don't do that. People go to the space station, which is not as far from you, again, as I am. But at some point in the late 1960s and early 1970s, 24 people were fortunate enough to travel the distance from the Earth to the moon. And so what that tells me is this picture shows the entire scale of firsthand, personal human experience throughout all of human history. It's contained in a picture of this scale for all of human history. And now Dawn passed the orbit of the moon the day after it launched. So we launched on September 27th, and on September 28th had the moon in our rear view mirror. So now let's bring in the next scale, which is the Earth's orbit around the sun. And of course, as the Earth goes around the sun, it brings the moon with it. So let me bring the sun into this picture. This is the sun. And on the scale of the sun, this is the orbit of the moon. And on the same scale, this is the Earth. The sun is larger than even the orbit of the moon. The sun is much larger than the entire scale of firsthand, personal human experience throughout all of human history. The sun is 109 times the diameter of Earth. The sun is 865,000 miles in diameter. From this, we can conclude the sun is big. Now, with that context, let me get rid of that stuff. I'm going to put the sun in the lower corner, and then in the other upper corner, I'm going to bring back in the orbit of the Earth, magnify it for a moment. That blue is the orbit of the moon. The blue is the orbit of the moon. Earth is much, much too small to be seen, excuse me. And Dawn passed the moon's orbit the day after launch, and in 2010 was as far as the sun, and over the course of its mission was 4 times as far as the sun, more than 1,500 times as far from Earth as the moon, well over 1,000,000 times farther than astronauts on the International Space Station. And in all honesty, I think this is amazing. I just think this is so cool. This is the same sun that has shone down on our planet for 4.5 billion years and is the source of virtually all of the energy we have ever had and may ever have. And this is the same sun that has so dominated human thought throughout all of human history and even longer, and has so influenced science, art, culture, literature, philosophy, mythology, and religion throughout all of that time. I mean, this is the same sun that's 1/3 of a million times the mass of our planet. This is the same sun that's our signpost in the Milky Way galaxy. And yet we have spacecraft that travel to the far side of the sun. And corny as it sounds, and it's okay, I know it sounds corny, but it's true. On Dawn and other missions I've worked on, when the spacecraft has passed on the far side of the sun, I've gone outside and put my thumb up and blocked out the sun and thought, gosh, we have a spacecraft out there on the far side of that sun. And when I say we, I don't mean me. I don't mean the Dawn team. I don't mean any of the teams that I have or the people I work with at JPL. I don't even mean the entire engineering and science community. I mean all of us. To me, these are missions of humankind. I think everybody shares in missions like this. Everybody who's like all of us here, all of you and like me, who's ever looked up at the night sky and wonder, right? Anyone who's ever longed to know the cosmos, had any curiosity about the nature of nature, right? I think we all share in missions like this. And that to me is really what's coolest of all about these kinds of missions. And so that raises then the question, how do we do that? Well, we start by putting the spacecraft on top of a huge bomb and hoping it doesn't blow up. Because as you know, these missions often end in really quite beautiful explosions. And sometimes you can see the debris raining down and setting cars on fire at Cape Canaveral or things like that. It's not the way you want your mission to go. And this is one of the most stressful parts of a rocket scientist's career. But fortunately, we didn't have that kind of start, although it was a beautiful launch. But we launched Dawn. In fact, at dawn, you can see the sun rising there just under the 734. We launched from Cape Canaveral and got the mission off to a very nice start. And once we got in space, then I'll show you the trajectory we followed, where here again, to orient you, we've got the sun in the center, the orbit of Earth shown in green, and you can see here where Earth was when we launched. And as we follow along the trajectory, where the path of the spacecraft is this nice chameleon xenon blue is where we were thrusting with the ion engine, and where it's darker is where we were coasting. So we coasted for a while and then operated the ion engine a little bit to check the ion engines out and do some other tests. But then we got into a pretty regular pattern of thrusting with the ion engine most of the time. And for specialists, I'll just tell you that the software that generated this trajectory actually, for technical reasons, exaggerates the durations of these short periods of coasting. So in fact, we actually thrust more than is indicated there. These periods are all much shorter. But the point is, you can see we're thrusting most of the time, spiraling outward from the sun. We coasted as we flew by Mars, slowed it down, sped Dawn up, continued thrusting, spiraling outward from the sun until we got to Vesta, went into orbit around it. We did a lot of thrusting in orbit around Vesta, but that's not shown here. But of course, the focus of our effort was taking those pictures and other cool measurements. Then we broke out of orbit, traveled again for 2.5 years till we got to Ceres, went into orbit around it, stayed with Ceres, again, collecting a wealth of measurements until the mission concluded a few years ago. And Dawn remains in orbit around Ceres now. I'll tell you more about that later. But the problem is when you see a picture like this, it's flat and it's static. And it's easy to forget that the solar system is constantly in motion. And so hoping that it'll work okay, I want to show you, work okay in Zoom. I want to show you an animation. And so let's start by orienting ourselves. This is the arrangement of the solar system in March of 2007. So here's the orbit of Earth, blue for Earth, the orbit of Mars, red for Mars, Vesta, and Ceres. And so we launched in September of 2007. So when I start this, you'll have a few seconds to sort of synchronize your view before the launch actually occurs. So we launch in September. Then you can see the spacecraft departing Earth, firing its ion engine. Vesta is going to complete another full rotation, a full revolution around the sun before we get there. You can see we flew by Mars. And Ceres still has more than another revolution before we get there. But here, as we get into 2011, we close in on Vesta. Finally, in July, go into orbit around it, spend 14 months there, taking all of our measurements. Then in September of 2012, fire up the ion engine, break out of orbit. It looks in this depiction like we're close to Ceres, but it's 2.5 years and 950 million miles of interplanetary travel to get to Ceres. Fortunately, I always feel gratified because every time I run this animation, still get into orbit around Ceres, because that was a long, hard climb through the solar system to get there. Dawn eventually does get into orbit and stayed there and continues even in orbit around Ceres now. And once again, this mission would have been not just difficult, but truly impossible without ion propulsion. And now you may be wondering, I've told you a bunch of times how important ion propulsion is, but you know what? You never heard of me before. You have no reason to believe me. I don't bring any credibility here. For all you know, I'm just somebody else who wandered into this Zoom meeting and clicked on the wrong part of it. And so I'm showing my camera here. And I hope I don't fall asleep during whatever else is going on here and embarrass myself. You don't know that you have any reason to believe me. And so I want to show you something from some people in whom I think you can have confidence. These are people whose job it is to think about what's important in technology and the future. And these are people in whom we can all have confidence. Now, normally in my talks, I would show you a video and you could hear them say it. I don't think that will work very well in Zoom. And so I apologize that I have to do it a little differently. But you can still appreciate what they have to say. And I'm starting with the context for who they are and when they said it. So it's the Star Trek episode, Spock's Brain. And in that episode, at one point, the always efficient bridge crew, when they're seeing a new ship, we hear the report that phaser banks are standing by. The range is 43,000 and closing. So just as you would do if you were captain, you would walk over and ask Mr. Spock what he reads, and Spock reports configuration unidentified, ion propulsion, high velocity, though of a unique technology. So Kirk, after walking by Uhura and giving her some more instructions, asks for Scotty's assessment, and Scotty says, "It beats me, but isn't she a beauty?" Kirk notes, "It's an interesting design." And Scotty, who has a little bit better Scottish accent than I do, says, "I've never seen anything like her. And ion propulsion at that. They could teach us a thing or two." And in fact, if you have the stomach to sit through much more of this episode, later on, you can hear Captain Kirk say to the bridge crew, "Advanced ion propulsion is beyond even our capabilities." But you know what? It's not beyond our capabilities now. And in fact, this episode was the first time I ever heard of ion propulsion. My older brother watched Star Trek when it was on in reruns, and I have a vague recollection of seeing this episode And it never occurred to me that I would grow up, if I ever actually did grow up, and actually get to work on a mission that uses ion propulsion. And if you've ever seen a TV show called How William Shatner Changed the World, or you even, there are excerpts of it on YouTube with me in that William Shatner show talking about this, and you can see those excerpts, some of those excerpts of Kirk and Spock and Scotty talking about how remarkable ion propulsion is. So what comes after Dawn? Well, it exceeded its expected lifetime and stopped operating in October 2018 after more than 11 years of space flight. But the spaceship will remain in orbit around Ceres for centuries. So we left it in this orbit where it goes as high as 2,500 miles and then dives down to just 22 miles above the ground. That's how low we got during the mission. That's only 3 times your height if you travel in an aircraft across the United States. And it makes this orbit every 27 hours. And we left it there because Ceres has all of the ingredients that are important for life. It has energy. We discovered organic materials. I told you it has water. It has other things that are important for life. So we didn't want to contaminate that pristine environment with our organically dirty spacecraft carrying materials from Earth. And so we left it in that orbit, even though it's no longer operational. But the data that we collected will be analyzed for decades, and future spacecraft will go back to Vesta and Ceres. In fact, we're even studying one to go to Ceres now. And of course, new deep space missions will use ion propulsion for generations. I mean, it's now a reliable technology. And of course, other things will happen in the future as well. I don't need to bore you with every imaginable detail. Instead, I will just thank you very much for your attention. I appreciate your letting me tell you about the Dawn mission. And I will just add one more thing. Sorry, that is, if you enjoyed this presentation, and I hope you did, I will put in a pitch for the same thing that Dave did at the beginning. That is, I gave a TED talk during the pandemic. So I actually had to make the video at home by myself with just an iPhone camera, things like that, with just my wife to help me set it up. But you can find it there at tinyurl.com/TEDMark. And I talk a little bit about Dawn, a little bit more about another mission, and just some other things that maybe you'd find interesting. But anyway, thank you again.
Well, thanks, Mark. That was great.
Thank you very much.
Another great talk. And I really, I did at least 3 spit takes. I was drinking hot tea.
Well, it's a good thing you had your camera off.
Yeah, it's a very good thing I had my camera off and I wasn't wearing a good shirt. We have several questions, and we were lucky to have Marianne with us tonight, who is always asking us a ton of questions. The first one that she asked was, how do we know that the liquid on Ceres was water? Couldn't it have been some other liquid substance that left the salt flats?
Well, that's a good question, but there are multiple lines of evidence that it was water, one of which is simply we can see the spectral signature of the water. The density matches for water, as do, and we see, I referred to the spectral signature, but really we see many minerals which are formed only in the presence of water. I know we're already running a little late, so
That's okay.
Well, I was going to say, I won't take the time to explain what I mean by the spectral signature, but it's a mechanism by which astronomers, and perhaps some even of the amateur astronomers here, can detect the chemical composition of something that you're looking at. And so these multiple lines of evidence show that it just had to be water. And so we have very high confidence in that.
Arlene asked, do either of these two bodies have any sort of magnetic field?
Well, that's an easy one because I don't know. Well, Dawn had many sensors, but it did not have a magnetometer.
Oh, interesting.
We carry the instruments we can. We would love to know, both because what I didn't talk about is we measured the internal structure of these bodies. And so we know that Vesta has a dense iron nickel core, just like your planet does. It's no longer molten like Earth's is, but it's very large. And so that suggests the possibility of a magnetic field there. And Ceres, because of course of having liquid water with ions in it, the motion of that also could cause a magnetic field. So it's the right question to ask, right? But we don't know, so we'll have to wait for the next mission.
Here's a question I was wondering about as well. How do we know that the meteorites that you showed, including the one that landed in your box, how do we know that those came from Vesta?
Well, again, there are multiple lines of evidence, but here also, so now I will say a little bit more about the spectroscopy, because so here again is the meteorite. Hope you can't really see much detail. There's the back of the box, so we can't see much more detail than that. When we look at the infrared light, so that's a wavelength of light that our eyes can't detect, but we know it's there, just like there are wavelengths or frequencies of sound that we can't detect that dogs can. When we break up that light, like with a prism, just like when you break up white light with a prism, you get literally the colors of the rainbow. When you do that with infrared light, it carries the signature of the material that it reflected from. So it's like a fingerprint. And so by measuring the infrared reflected light from Vesta, astronomers were able to get basically a perfect match or a near perfect match with this large class of meteorites that had been found in the lab. But
so this was all through remote detection.
Well, that's how the initial case was made. And in fact, it was made in the very late 60s, early 70s, when the military had developed these infrared detectors. But when they became available to the astronomical community, like all of us, astronomers started taking these infrared spectra and detected that. But it wasn't clear enough until Dawn got to Vesta, was able to get more accurate spectra and make measurements with other sensors that matched the more detailed measurements the scientists had made of these meteorites in the laboratory to clinch the case. I know I tend to give very wordy answers. If I can just give you one more part.
Sure, please.
I told you that this impact that excavated this material at the South Pole, sprayed out a lot of material. Some of it landed on Vesta, some of it landed, in boxes on Earth. But some of it went into orbit around the sun and is still there as bigger pieces. And astronomers have detected a bunch of smaller asteroids that are now called vestoids because they actually match the spectrum of Vesta, and they trace almost like a trail of breadcrumbs from Vesta to Earth. And if you add up all of the volume of those, you get a number that's surprisingly close to the volume of that crater that was excavated there.
Oh, that's
so
amazing.
A bunch of really cool connections.
That's great. Thank you for the answer.
I have a question about, we have Vesta. Do we have any evidence for anything from Ceres on the Earth?
No, we do not, but scientists have looked for it. And there are multiple possible reasons for that. I mean, obviously there are reasons, we don't know what they are, but multiple possible ones. It could be things like the material that Ceres is made of doesn't have the structural integrity to survive the being blasted off the surface, traveling, excuse me, for many millions of years. Excuse me, I apologize.
Sorry.
Through the solar system, surviving the trip through the atmosphere. There may not be as, so part of it is where Vesta is located in the asteroid belt is, I know this is going to sound a little obscure, but I'll just sling around some terminology. It's energetically, they're energetically efficient mechanisms for gravity to perturb or distort the orbits of material lofted from Vesta to help get it near Earth. Maybe those mechanisms don't work as well from where Ceres is located in the asteroid belt. And the other thing is, it may be that we have a bunch of those materials and have not yet recognized them because the spectrum of Ceres is not as obviously distinct and unique as the spectrum of Vesta.
Great.
Maybe it's something else.
Thank you for that answer. Do either of these two bodies, are they massive enough to have any semblance of an atmosphere, however small?
Well, they don't, neither of them does have any, no, they're not massive enough to have an atmosphere. They're even less massive than the moon, which can't hold a significant atmosphere. But still, I'll just mention, they are quite massive compared to typical asteroids. I showed you in size how massive they are, but or maybe you don't know, there are millions of bodies orbiting in the main asteroid belt. Ceres has something like 35% of the total mass of the main asteroid belt.
Wow.
Just in that one body.
Wow.
Vesta has around 10% of the total mass of the main asteroid belt. So those two bodies together are nearly half of all of that mass distributed among millions and millions of bodies, but not enough to have a significant atmosphere. So if you accept my invitation to go on that hike there, I'll count on you to bring your spacesuit.
You're on.
Yeah.
Okay.
Yeah, I'm up for the hike.
Okay.
That sounds great. I think, there were several other questions that were asked, but it sounds like you answered most of them as a result of the answers you already gave. Here's the famous question that we've heard in many different contexts. What is the current size requirement to be called a planet?
Oh,
There is no size requirement for being called a planet. The definition of a planet is not directly related to size. The requirement for being a planet or a dwarf planet is that the body be large enough. So I'm not going to give you the formal technical definition. I'm just going to explain it, I hope, is that the body's own gravity is enough to form a roughly, it's important that it's roughly, because even Earth isn't spherical, but a roughly spherical shape. So, smaller things like this, just happens to be an adapter for my computer, or this, or for that matter, you and I, we don't have enough gravity to reshape ourselves into something that's nearly spherical, right? But if you get bigger and bigger and bigger, your own self-gravity will cause you to make that shape. And a body needs to be a few hundred, at least, a few hundred miles in diameter to do that. But it's depends also on other things, including what it is made of, right? Its mass, because it's a self-gravity thing. And in fact, Vesta probably would have qualified as a dwarf planet, but after it's solidified in what presumably was a shape that would have qualified it to be a dwarf planet, it had this big punch in the South Pole, and it was then no longer able to reform itself because it cooled off and it was rigid. And so it doesn't meet the qualification.
But
So
Ceres kind of does.
not kind of,
Not,
it does.
yeah.
It does. There's no kind of.
Okay.
Ceres satisfies all of the attributes of a dwarf planet, as does Pluto. And the only difference between dwarf planets and planets is not their size. It's whether they have cleared the orbit of the sun around them.
Got it.
You say you get this question all the time. The simple fact is, most people don't like that definition. But okay, that's the definition.
All right, that was a good answer. Thank you. And it's a good thing this was a webinar, because as you were answering, Gerald was in the background giving a rant about dwarf planets, and actually he was in full agreement with you. And good, so I don't have to listen to.
I'll just tell you again, whatever you think about dwarf planets, I first of all, the universe isn't the way we want it to be.
Yeah.
It's the way it is, and just like in the late 1840s, vocabulary changed and they stopped calling Vesta and Ceres asteroids. Stopped calling them planets and called them asteroids. Vocabulary changes to keep up with our scientific understanding of the nature of the solar system. It's just words.
Yes.
The universe is the way it is. But I'll tell you, my big disappointment with the whole dwarf planet kerfuffle in 2006 is it was a great missed educational opportunity to engage the public in a discussion of what are planets, what are dwarf planets, what is the nature of scientific knowledge, how does it advance? I mean, why is Pluto any different from the myriad other bodies in that part of the solar system? People don't call Ceres a planet anymore. I mean, there's just all kinds of interesting questions there.
Gerald's
I'm not ranting, I'm just saying.
No, that's great. Instead we tend to get too fixated on words rather than on knowledge.
Concept,
and this isn't just in this topic. This seems to be a general social problem.
I live in the same country you live in.
Yeah, yes.
I'd like to remind everyone there was a time when the Earth wasn't considered a planet.
Well, that's true. All right. Well, you know what?
Can I just ask one more question?
Oh, by all means. Go ahead. Go ahead.
Mark, Dawn was such a successful mission. It begs the question whether there would ever be a super Dawn mission where we would do a survey of many more asteroids once we get a spacecraft out to the asteroid belt.
Well, so there could well be other missions that would survey them, as you said. Now, of course, we picked by design the two arguably most interesting bodies there because they're so large and massive. But in fact, another mission that I'm advising right now, you mentioned some of the projects that I'm overseeing or working with, but another one is called Psyche, Psyche, which is going to launch next year and directly inherits much of the technology and design and strategy from Dawn with the ion propulsion. And it's going to go to, so the mission is called Psyche, and it's going to go to the asteroid 16 Psyche, which isn't, of course, as large as Vesta or Ceres, but is still quite large and is possibly mostly made of metal.
Wow.
And could be, it isn't known, I mean, wait till 2026 when it gets there and we'll find out, could be a remnant core from a body like Vesta so Vesta survived that big impact that excavated the South Polar Crater, but Psyche might be left over from a similar body early in the solar system history that actually broke up when it was hit, and Psyche could be that leftover metallic core. Now, isn't that cool?
That
Very
is
cool. Very
cool. So that's a good follow-on mission right there.
Well, now I can't wait till 2026.
Me too.
Yeah, that's a good one. All right. Well, thank you everyone for your participation tonight. Thank you, Mark, again for another excellent talk, and I hope to hear more in the future. And Dave, thanks for everything you do.
And we'll have to invite Mark up to Chabot once we're
absolutely
after the pandemic and have him up and show him our wonderful telescopes. We'd love to have you.
I would love to do that.
You
I would
just
love
have to give us another talk, Mark.
It's an open invitation.
Okay, thank you. And
All right.
and everybody else for joining and letting me tell you about Dawn.
All
Thank
right.
you.
Take care now.
Bye.